So let's begin today's lecture by reminding ourselves of some of the results that we had in the previous lecture. So what we were able to do is to start with showing a picture of psi of x, a vector d3 p by 2 pi to 1 by square root of dp a p alpha u alpha p potential I p dot x plus b p alpha diagonal v alpha p exponential minus I p. We started from here, and the fact that the Hamiltonian operator written in terms of our written in terms of the operators, these fields psi bar, and then there was I times del I comma I psi minus m psi bar psi. We basically started from here and showed that our Hamiltonian will turn out, the Hamiltonian which is the space integral of this, so total Hamiltonian is d3x of this Hamiltonian, and what we find is that it was d3 p by 2 pi u 1 by square root of twice, I'm sorry, this is normal, now it is EP, and perhaps the sum over alpha of a p alpha diagonal a p alpha plus b p alpha diagonal b p alpha, and plus a constant which was insignificant. Okay, because what we have for total energy as an operator, this is just a constant term. It's an infinite constant, but what matters, this is a complex number, infinite complex number in general, and this is the operator. All the dynamics is computed using these operators, while this complex number, which is technically infinite, has no consequence in computing any physical quantities. So we, in our definition of H, we basically drop this. Okay, and then we go on to compute some of the simple things, starting from the simple commutators of this Hamiltonian with the four operators that we have, which is A dagger, and B dagger. We will start with computing the commutator such as H commutator with A B beta. This commutator, if I write, is H AP beta minus AP beta H. Write the expanded expression of Hamiltonian without the constant piece. Even with the constant piece, what happens? This operator will commute, the constant piece will simply disappear. So what you will have over here is d q by 2 pi q, because this operator thing I took as a p. Let me not take as a p. This is p, and this is, and this should be p. Here EP. Okay, so EP is part of the Hamiltonian, so it will remain as it is, and let's write the part of the commutator inside it. So let me start the big bracket. The first term has AQ multiplied to the right. So let's write the terms of the Hamiltonian, which is sum over alpha of AP alpha dagger AP alpha, to which from the right hand side multiplies AQ beta plus BP alpha dagger BP alpha, to which from the right hand side multiplied AQ beta. This is the H times AQ beta. From here I have to subtract AQ beta times the same term, so sum over alpha, and here I will have AQ beta AP alpha dagger AP alpha plus BP alpha dagger. But before that there will be AQ beta and BP alpha. Okay, so this is what we have. Now let's look at the terms underlined here. Okay, what happens since AQ anti-commutes with both of these operators, pure anti-commutation. So when I bring this guy over here, I have no sign change, and since there's a negative sign between them, these two cancels out. Okay, now in order to write let me again choose a different color. In order to write these two guys, okay, so let's write those two terms over here. So I have to bring alpha Q beta to the leftmost. Okay, or here in the second term AQ beta to the rightmost. Okay, so let me just say what I want to do. AQ beta AP alpha dagger AP alpha. Just focus on this term, and using the anti-commutator I can write this as, with a minus term, AP alpha dagger AQ beta. This will be in a different order. Okay, plus 2 pi q delta 3 p minus q. The whole thing is multiplied on the right hand side by a p alpha, because I did not touch this guy. Okay, so this remains as it is, so let's keep it like that. And still there is no cancellation, because here AQ beta is sitting in between. Okay, now AQ beta and AP alpha commutes, anti-commutes, sorry. So I just change this sign over there and bring it to the other side. The first term is minus AP alpha dagger AP alpha, sorry, this becomes plus, and AQ beta, and second term is 2 pi q delta q p minus q, and AP beta is to the right. Let me bring it to the left. Sorry, it is to the left. Let me write it as it is. And right here it is just AP alpha. I'm sorry, second term only has AP alpha. Okay. Now this term in the second piece has become similar to that term, and now it cancels out. All I have this with a minus sign, these two guys. So basically my this commutator has d3p by 2 pi q EP, and then sum over alpha, my apology, here delta alpha beta is also there. Okay, so what I have, because this is an anti-commutator, it has delta function 3-dimension and delta alpha beta also there. So things that will cancel out, this to cancel out, this to cancel out, I have minus 1 times 2 pi q delta 3 e minus q a p alpha delta alpha beta. Okay, so when I sum over alpha, this alpha becomes beta. When I do the q integration, okay, then this p becomes q, and this 2 pi 3 q's and all these things cancels out. So basically what I have is minus eq a p, I'm sorry, aq beta. This is what I get. Okay, so let me just write it here, the answer, that this particular commutator will be minus eq, the energy corresponding to the qth guy, aq beta. Okay, now if I do similarly commutator, instead of a, if I take a Dirac, okay, now this last two terms in yellow will still cancel, simply because a Dirac or b Dirac, a Dirac or a both commutes with b Dirac b, so this 2 goes away. Okay, now instead of having two a's over here, I'll have a beta Dirac and here also a beta Dirac. Okay, and then the cancellation, what I'll get is just the opposite term. So what I will have, without exactly showing, so let me first write what I got for the commutator. I got h a q beta, I got as minus eq aq beta. Without proving explicitly, I am saying that h a q beta Dirac is plus eq aq beta Dirac. Similarly, since h, expression of h, if you see, it's completely symmetric between a and b. Okay, there is no difference between, if I just replace a and b, there is no basic difference. So if I have to compute commutator of h with b q beta, I can blindly follow the same steps and I'll get minus eq bq beta and h bq beta Dirac equal to plus eq bq beta Dirac. Now what is the importance of this 4 commutation relations? So note that a's and b's are objects that they commute or the anti-commute with each other, with anti-commutator between a and a Dirac and b Dirac. The Hamiltonian is not an anti-commuting object. It's made out of 2 anti-commuting objects, so overall it's a commuting object. So with the commuting object, between the commuting object and an anti-commuting object, usually we define a commutator, and this comes out to be very nice numbers. They're very nice expressions, and these are exact expression what you would expect from the raising and the lowering operator in a harmonic oscillator. So to say a Dirac q beta increases the energy of the state by amount eq. Okay, so based on the definition of my h over here, I can just say that h acting on 0 is 0. This is to another way of saying that I am dropping the constant, and that happens because ap alpha, this is because ap alpha acting on vacuum is 0, it kills its annihilation operator, and bp alpha acting on 0 is 0. So both of them killing the ground state, and this constant piece we are setting to 0. So with this understanding, okay, here what I say is that I can ask what is the energy of a state defined as A Q beta dagger acting on 0. So this is a one particle state. Okay, if I want to compute this, okay, I don't know how H will act on this, I don't know what this state is, but what I know is that H times AQ beta, okay, this product of this operator is nothing but EQ AQ beta dagger plus I have AQ beta dagger H acting on vacuum. Now H acting on vacuum, we have set it to be 0. So this just gives me E times AQ beta dagger 0 state. So whatever is this state, its energy is EQ. Okay. And of course the vacuum was a 0 energy state by construction. So what I'm seeing over here, that AQ beta creates a particle. Likewise, exactly similarly, the energy of the state B Q beta dagger acting on vacuum is, I'm skipping the step, is again EQ times BQ beta dagger. So whatever is this state, which is generated by raising the vacuum using a BQ beta dagger, so that one particles or one antiparticle state also have the energy which is positive energy. That's the important thing to know, that antiparticle also requires a certain amount of energy to be created. Okay, that was very important step for choosing the anti-commutators between A and B, and that guaranteed that my so-called negative energy solutions are actually the positive energy solution of the Hamiltonian. Okay, and my V spinner is actually a positive energy excitation from the vacuum. So one has to choose a vacuum appropriately. That is given by the H acting on vacuum to be 0. Okay. So, and likewise, what A does is that it annihilates a particle of momentum Q and spin beta and energy EQ. So it reduces the energy of the system by amount EQ, and same for the B Q beta, it reduces the amount of energy or the eigenvalue of the H operator by amount EQ. Okay, so that again I'm not showing because it is similar to the exact expressions that we use for the harmonic oscillator. Okay, so next we move on. So this is about the Hamiltonian. Next we move about okay, so I think before moving to that, since we have this relationship, we can immediately say that the Schrodinger picture that we started with, okay, this is my psi. Okay, so now if I want to write the Schrodinger picture thing, psi of t and x, I need to do a time evolution. Okay, so the time evolution done by this simple operator, this would be exponential I h t. The Hamiltonian is a generator of time translation. Psi of x, the Schrodinger picture thing, exponential minus I h t. This is how I require. Basically what you will see over here, let me make this line smaller. Okay, so what you will see over here, that basically this involves exponential I h t a p beta exponential minus I h t, and if I expand this, this is nothing but a p beta exponential minus I e p t. Okay, and if I had I ht a b beta dagger exponential minus I ht, that will give me a b beta dagger exponential I e p t. So look at the sign of the commutator. If the sign is negative, you have exponential minus ept, and if the sign is positive, you have exponential plus ept. Okay, so now if I, because that's the only operator that transforms non-trivially under the Hamiltonian operation, other things are just complex numbers. So in this operator Schrodinger picture, this a's will get an extra phase, so the a will get exponential minus ip dot x, and b dagger will get exponential ip dot x, because b gets exponential ip dot x, b dagger will get exponential plus ip dot x. So that basically changes this guy, Schrodinger guy, into the Dirac in the Heisenberg, by just the only thing that happens is that this exponential factor, instead of being a 3-vector product, becomes a 4-vector product. Okay. Again, I'm not writing the details because I've already written the expression for this in previous lecture. These things will be written, or maybe I just, for completeness, I write d3p by 2 pi cube 1 by square root of twice ap sum over alpha a p alpha, the same thing will come, and u alpha p exponential minus I p dot x is a 4 product, b p alpha dagger v alpha p exponential minus I p dot x. This is also 4-vector product. Okay, so next we move on to use this Schrodinger, the Heisenberg picture of guy to find the propagator. How? What is the amplitude of propagation from point y, starting from point x to, starting from point x to point y? How does this go? Okay, so I want to compute the transition probability of a particle, actually probability amplitude of a particle for moving from point y, starting from point y to going to point x. So how do I do that? So first I have the vacuum. Okay, then I create a particle. Okay, so create a particle or antiparticle, that depends on which operator you are using. So let's say psi bar at y. Let me write the component also. It's just for, I'll use the exact notation. So this is my initial state. The final state, that where it reaches. Okay, so there a particle came, so I have to create it using again on the vacuum, created with psi x. Okay, created with psi dagger x, you can say, and then take a complex conjugate to get into the final state. So I have psi x a. So this is roughly like final state, initial state. Okay, this is my initial state, and I create a final state, take a complex conjugate and put it over here. Okay. So while taking complex conjugate, actually I'm taking the Dirac conjugate, multiply by gamma 0 to get rid of this gamma 0. So this is the quantity I want to compute. Okay, and very important thing over here, that I want the vacuum expectation value. So as we have in the previous slide, okay, as we have in our previous slide, psi of x, here x means the 4 vector that I'm interested in. Here x and y are the 4 vectors. So, and since this happens here, this is the case very specific to that, that x naught happens after y naught. That means at y, vector y, I had at some time y naught a particle that happened first, and then it propagated to x naught. X naught happened later. Okay, so if that is the situation, I want to consider what this quantity is. Okay, this I want to compute, so this remains the vacuum expectation value, but this I want to compute basically. So let's leave that. Okay, no, let's keep all these things here. So here let me write for x naught is greater than. Okay, this is the situation. What I have is vacuum expectation value of, let me start writing the expression for xa, psi of xa and psi of xb. So this is going to be repeated too many times. d3p by 2 pi q 1 by square root of twice ep sum over alpha and a p alpha u alpha of p exponential minus I p dot x, this is a 4 product, plus b p alpha diagonal v alpha of p exponential I p dot x. This is my 4 product again. This is the first term, and let me write this whole thing because this is a spinner. I want the 8th component of that spinner. That's my psi a. And what I mean by u alpha p is a spinner. I want the 8th component of that, and this has to be multiplied. Me write a here, multiplied by d3q by 2 pi q 1 by square root of twice eq sum over beta a q beta dagger, because complex conjugation is taken, u beta bar q exponential I q dot y. Okay, note that it's at position y, plus b q beta dagger gone. Now I'm taking the conjugate, and I have b bar beta q exponential minus I q dot, and I want bth component of it, and then I want to project onto 0. So as we can see, there are 4 terms. Okay, 2 terms coming from each, but it has to connect from 0 to 0. Okay, so without writing all the detailed expressions, okay, or maybe since it is the first time I write, so what do I have over here? I will take all the integrals and summations outside. Maybe summation I'll keep inside. So d3p by 2 pi q 1 by square root of twice ep d3 2 by 2 pi q 1 by square root of twice eq. Okay, and then start 0 summation of alpha beta of, now let's look at the operators. So I have a p alpha a q beta dagger. Okay, this is what gonna sit between 0 and 0. Okay, this will be there, and let me write what it comes with. It comes with u alpha p u bar beta q, and here 8th component of that and bth component of exponential minus I p dot x minus q dot y. Okay, and then I have terms like a from here, a p alpha, and then I have b q beta. I'm not even going to write these two terms plus B alpha Dirac AQ beta Dirac. Again, I'm not going to write these terms. And then we have B alpha Dirac BQ beta, and again I'm not going to write this down. I have 0 over here. Now, why I did not write this term? Because I know they are going to give me 0. So B acting on 0 gives me 0. So this term is gone. Okay. So this acting on this gives me 0. Okay. Here this guy acting on this gives me 0. Here again B acting on this gives me 0. Okay. The only non-zero term that I have is coming from the first. So let's write that in the next page. That for, again, just to reminder, x naught greater than y naught, I have 0 psi x a psi bar b y. Okay, and that happened to be d3 b by 2 pi q 1 by square root of twice ep d3 q by 2 pi q 1 by square root of twice eq, and I have this multiplied by sum over alpha beta u alpha p u bar beta q and a b element of that times 0 a p alpha a q beta Dirac 0. Okay, times I have the exponential factor minus I p dot x minus q dot y. Okay, now what this quantity is? Okay, so I can write, I don't know how to write this because the state created by a Dirac q, I haven't studied it, but I know the commutator or the anti-commutator in this case. So what I can write this as 0 and with a minus a q beta Dirac a p alpha plus 2 pi cube delta 3 p minus. Okay, now here a acting on this gives me, the first term is gone, so that gives me just 2 pi cube delta 3 p minus. Okay, I'm sorry, there's one more thing, delta alpha beta. Here is alpha and beta there. So this is what sits over here, and once that happens, then I perform a summation over beta to get all the betas converted to alphas, and I do integration over d3 cube, and 2 pi cube, this cancels out and q becomes p because of this delta function. So what I have over here, this particular quantity is d3 p by 2 pi cube, and when p and q become same, I have these two factors becoming same, so 1 by 2 ap that I got. Here p and q become same, this particular term just becomes summation over alpha because beta is gone, taken care by delta alpha beta, u bar alpha p, sorry, u alpha p u bar alpha p. Okay, this is what I have, x along with exponential minus I b x minus q is same as p. Okay, now once I perform this summation, and okay, I'm sorry to say this is a bth term, because a and b were the two elements of the two spinors we started with, so this becomes d3 p by 2 pi q 1 by cp, and this becomes p slash plus m a bth element of exponential minus I b dot x minus. Okay, and I can write this in terms of a derivative operator, d3p 1 by twice p, and the derivative operator you can easily check is I times del slash x. X says that it is the derivative with regard to x, not with regard to y, plus m of exponential minus I p x minus y. Okay, in other words, I just write a b term, I del slash x plus m, this is the operator, a bth element of this is acting on d3p by 2 pi q 1 by twice cp exponential minus I p x minus y. So this is what this term. Okay, now I can do this entire computation again and ask for a different question. In this scenario, if I just swap these two guys, okay, a and b guys, I'm looking for a scenario, so 0 psi bar b y psi a x, and we are basically considering the situations as we did in scalar case, that do we have connections outside the light cone, and this would say exactly over the, like over there, that yes, we will have connections outside the light cone. In fact, every retarded Green's function over here will be exactly connected to the Green's functions in the scalar case. So here, just to say, if I start my computation from here, okay, so what do I get? So of course x and y are interchanged, and a's and a daggers, various things are interchanged. So in place, so if you just look my expression over there, okay, so here the four guys were there, and I marked that the guy in yellow box is what going to contribute. Now suppose this a and b's everywhere has appeared in opposite order, because that's what will happen if I exchange these two terms over here. So now this first term will no longer contribute because a is sitting to the right, but the second and third term will still be 0. It is the fourth term, okay, the fourth term that will start to contribute. So now I can come over here and say what my fourth term was. So this is that I can directly use it. So it had v alpha p v bar beta. Okay. And let me not put that, and a and bth element of it, along with exponential I p dot x minus q dot y. No overall minus sign. In the first case, overall minus sign was there. But the summation of v with the v bar will give me a minus p slash. Okay. So this p being opposite sign would kind of taken care of. And eventually what I get in this particular case, I simply write that directly, is minus I del slash x. I'm still taking the derivative with regard to x, plus m of d3p by 2 pi q 1 by twice dp exponential of minus I be y minus x. Okay, or let's just say x minus y without the minus. Okay, that's what this extra sign will come over here from. So this is the expression when I have the two guys in the different order. So these two guys we have computed, which we require to compute our retarded Green's function, so to say. Okay, so what is my retarded Green's function for this? S R a bth element from x minus y is theta of x naught minus y naught. So that just makes sure that x naught is greater than y naught, but then it takes the expectation value of commutator, okay, which is, instead of writing a commutator, sorry, anti-commutator, I simply write this psi bar psi a x psi bar b y plus psi bar b y psi a x is this quantity you take in both possible order when x is greater than x naught is greater than y naught. This particular order if you take, and what you get over there is this theta of x naught minus y naught. Okay, the first term is I del x slash plus m acting on, okay, both the term has this, so let me remove this, don't need this. Okay, so this operator acting on an integral d3p by 2 pi q 1 by twice ep exponential minus I p x minus y. That's coming from the first term. The second term has exponential I p x minus y. Okay. Now I can change the order in which they come, and I can, even though this derivative with regard to x naught is sitting on the right hand side, this whenever x naught is greater than y naught, not when they are equal, whenever x naught is greater than y naught, I can, it's a constant function again, so the derivative will be 0. So basically I can commute these two guys, and I can write this as I del, pardon me, and write this as I del x slash plus m acting on theta naught minus y naught d3p by 2 pi q 1 by 2 ep of exponential minus I p dot x minus y minus exponential I p dot x minus y. Okay, and just complete this sentence plus m, and this is your retarded Green's function of the Klein-Gordon theorem, this square bracket. Okay, so this is my, okay, everywhere you could have written AB. This is the ABth term. So I have my S r of x minus y without the AB term is I del x slash plus m dr x minus, and this retarded Green's function, one can also confirm that this is a Green's function of the Dirac equation of motion, right? So for showing that, what I need, what is the equation of motion for Dirac field point? It is I del x, let's say taking derivative with regard to x, minus m acting on S r x minus y. Okay, so that just becomes I del x slash minus m acting on I del x slash plus m acting dr x minus y. Okay, and this just becomes del x slash with a minus sign minus m square, and the cross terms cancel, dr x minus y, and del x slash will be del x square. So this is up to a sign is del square plus m square acting on dr x minus y, and I know what this is because this is already Green's function for this guy. So this basically gives me I times delta 4 x minus y times, and so this SR x minus y that we have computed is indeed the retarded Green's function. Okay, and basically we don't need the retarded Green's function because when we write this integral, so okay, let's first write the integral for this. Okay, so first we saw that this is the Green's function, so to say, and Green's function is a propagator that you already know. So let's just start by saying that SR of x minus y could have been represented in a Fourier transform as d4 p by 2 pi power 4 some s twiddle of retarded of p exponential minus I p x minus y. Okay, now apply my equation of motion both sides. Okay, so this must satisfy the same equation of motion that we have just computed above. So if this is the Fourier decomposition of SR x minus y, then I del x slash minus m acting on SR x minus y is just d4 p by 2 pi power 4 SR twiddle p, or maybe SR twiddle p is sitting like I'm acting mind. So this could be a matrix, and this doesn't have x in it, so I can write this phase factor in the front. So I can let me write I times del x slash minus m acting on exponential minus I p dot x minus y, and then s twiddle r p, because in general this could have been matrix. On the left hand side is matrix, so this could be matrix, and I don't want to confuse the this del matrix, which is also an this del slash is also a matrix, so that will cause a problem since I don't know what is the matrix structure of that. So I'll put it like this, and it is pretty clear that when I del x acts on this guy, what it gives me d4 p by 2 pi 4 and the p slash times I, so this is just gives me p slash minus m, it gives me times, and this is a constant, this is a complex number, so I can write times s r p function minus I p x minus y. Now on the right hand side, if you see, it is just I times this delta function times the identity matrix. So somehow this particular quantity must be equal to I times identity matrix, that it goes outside the p integral. Okay, and all I have is this d4p by 2 pi 4 and ip x minus y, so that will just give me a delta function. Okay, so for that to happen, tells me that r twiddle of p is nothing but I divided by p slash minus m, or I p slash plus m divided by p square minus. Okay, it's very weird to write a matrix in the denominator. We multiply by p slash plus m in the numerator and denominator. Numerator becomes this p slash minus m square times an identity matrix. Like inverse of identity matrix is 1, so I can write SR. Okay, in this particular case, if you just compare this particular expression here, if I write so this expression, okay, so here if I replace SR divided by this particular quantity and compare with the SR expression that I had here, okay, over here. So here you see I can write this 1 over 2 EP and all these things combined to d4p, okay, only if I perform a contour integral of p naught. So here I choose a very particular contour where this p square equal to m square. So in the p naught case, in the p naught complex plane, there are two poles on the real, okay, and this particular thing amounts, this particular integral value amounts to choosing a contour which goes like this and closes above. When x naught is equal to, when x naught is greater than y naught, then it closes above. This is for x naught greater than 1. And now all the argument of the scalar field theory repeats, because we are writing everything in terms of the this drs, which is the retarded Green's function of the scalar field theory. So clearly from there, instead of repeating all that discussion, we can simply ask that instead of retarded Green's function, can I write the Feynman Green's function, the Feynman propagator? Feynman's propagator. So what it would be? So s f of x minus y would be d4 p by 2 pi power 4 I times p slash plus m, and using the Feynman prescription, I'll have p square plus m square, so p square minus m square plus I epsilon exponential minus I p x minus. So this again in the p naught plane amounts to two such propagation, two such poles, and this time using the Feynman's prescription, we go below this and we go above this, and either we close above or below depending upon whether x naught. So here again x naught is greater than y. Okay, so I pick up only one pole in this, not both the poles. So not picking both the poles, what it amounts to is that when I'm writing my SR, I have two terms. Pick the one pole, it means pick only one term of this, which is the first term. And in the case of x naught greater than y naught, I should have had only this term. But when y naught is greater than x naught, then I should have had only the second term. That is the right thing to ask, because here the question asked itself was wrong, because when x naught is greater than y naught, could I have talked about the second operator? And that is the main thing, that although quantum mechanics says add all possible combination and in whatever orders they can come in, but what causality says that you have to maintain the causality. Whatever came first, those operators should act on the vacuum first, followed by the guys which came later. Okay, so this I epsilon prescription for x naught equal to y naught will, when you close the contour above, it picks up only this left hand side guy, and when you close the contour below, it only picks up the positive pole. Okay, so the way to write this particular guy in terms of operators is that this is 0, psi a x psi bar b y 0 when x naught is greater than and equal to minus 0 psi bar b y psi a x 0 when x naught is less than. Okay. So this is the way we write it. Okay, which in other words is 0 time ordered product of psi a x psi bar b. Okay. And here this is I'm talking about abth component, perhaps make it consistent. So this is how the Feynman propagator would work. Okay, this is time ordered product is very important for causality. And extra thing that happens for fermions, that when you change the order, when the notation for time order operator is that whichever order it is written in, that is comes with a plus sign, and any swap that we need to maintain the time order, that each swap will take a minus. Okay, so if you have even number of swaps, then it is a plus sign again. Here only two fields are there, but in general we can have more than two fields. Okay, so just want to repeat one last time is that when we talk about the propagators or any different ordered products for fermions, all the rules are exactly same. Even for the contractions, which gives me the propagator, all the rules will be exactly same as the case of scalar, except that when we swap two fields, we have a minus sign, because these objects are made of A's and B's and they are anti-commutator. So it's the anti-commutator that comes over here. So this, when we're dealing with a string of fermions sandwiched between 0 and 0, then we again need Wick's theorem to see how to compute it. Instead of using commutators as we used for the case of scalars, here we have to use anti-commutator, and it's the anti-commutator that says any swap of the fields will give me a minus sign. So the Wick's theorem and a Yukawa theory using computation in Yukawa theory is what we will do next in the next lecture. And here we stop in case of Dirac propagators. And yeah, so next lecture would be about the Wick's theorem for fermions and how do we deal with a given theory, given interacting theory, which is the proper Yukawa theory. In quantum field theory 1 course, you have already discussed how to deal with a pseudo Yukawa theory. So there was two fields interacting and both were scalars basically. So here will be a proper Yukawa field where the fermion is interacting with a scalar. So that would be in the next lecture.